Large language models, or LLMs, have become incredibly useful in many applications, from writing and translation to data analysis. However, one major issue that holds them back is something called hallucinations. This is when the model generates content that's not factually accurate or doesn't match the given context. For example, if you ask about a singer born in New York, the model might incorrectly say it's Elvis Presley instead of the right person. This paper, titled, "Why and How LLMs Hallucinate: Connecting the Dots with Subsequence Associations," dives deep into understanding and tracing these hallucinations. The authors, including Yiyu Sun, Yu Gai, Liji Chen from the University of California, Berkeley, and others from the University of Washington and Stanford, argue that hallucinations stem from how the model handles associations between parts of the input text. Their key idea is that hallucinations occur when certain misleading or hallucinatory associations in the model's internal workings overpower the correct, faithful ones. To tackle this, they introduce a new framework called subsequence association, which helps systematically trace where these errors come from. First, let's break down why this is important. LLMs, like those based on decoder-only transformers such as GPT models, are trained on vast amounts of data, learning patterns and connections between words and phrases. But because of the way they're built, they can sometimes prioritize incorrect patterns. For instance, if the training data has rare or biased examples, the model might associate a subsequence, like a phrase about a singer from New York, with the wrong name, like Elvis Presley, even if that's not the most common or accurate link. The paper explains that decoder-only transformers essentially act as subsequence embedding models. This means they represent and process parts of the input sequence, like smaller chunks of text, through their linear layers. These layers encode the relationships between inputs and outputs, creating associations that influence what the model generates next. Through theoretical analysis, the authors show that when a hallucinatory association is stronger, perhaps because it's more frequently reinforced in training, it can override the correct one, leading to errors. To make this concrete, they propose a tracing algorithm. This algorithm works by analyzing the probabilities of hallucinations in different randomized input contexts. Imagine you have a prompt like, "The successful singer born in New York is called L." The model might output, "Elton John," correctly, but sometimes it hallucinates and says, "Elvis Presley." The algorithm identifies the specific subsequences, those smaller parts of the text, that cause this by shuffling or modifying the context and measuring how the output probabilities change. For example, in their experiments, they tested prompts and found that certain phrases, like, "born in New York," might trigger a strong but incorrect association with Elvis Presley, due to spurious correlations in the training data. By randomizing parts of the input, the algorithm can isolate which subsequences are causally responsible for the hallucination. This is a big step up from traditional methods, like gradient-based attribution or perturbation techniques, which only give token-level importance scores without showing real causal links. The authors backed this up with empirical evidence. They ran tests on various LLMs and found that their method not only outperforms standard attribution approaches but also aligns closely with what's actually in the model's training corpus. In one case, they looked at sampled outputs for a prompt about a singer and calculated probabilities, like a 52% chance of generating Elvis Presley versus 45% for Elton John. By applying their tracing algorithm, they could pinpoint the exact subsequences driving these errors, such as misleading patterns from the data. This framework is powerful because it unifies many previously identified causes of hallucinations. Things like overconfidence, where the model is too sure of itself, decoding randomness, which introduces variability, or even the reversal curse, where the model struggles with reversed information. All these can be explained through the lens of competing associations. The paper shows that by understanding these dynamics, we can better diagnose and potentially mitigate hallucinations in future models. One interesting example from the paper involves a prompt like, "The successful singer was born in New York. He never watched The Lion King. He is L." Here, the probability of generating Elton John jumps to 90%, suggesting that additional context strengthens the correct association. But if you change it to something like, "Following Victor Manuel's success, he is L," the model might still hallucinate due to conflicting associations. This highlights how context matters and why their algorithm, which tests multiple variations, is so effective. Overall, this work provides a robust tool for researchers and developers. By offering a way to trace hallucinations back to their roots, it helps in debugging and improving LLMs. The authors have even made their code available on GitHub at the link provided, so others can build on this. This approach not only connects the dots between various causes of hallucinations but also paves the way for more reliable language models in real-world applications.